So it really is a pleasure to be here on behalf of the CDF collaboration and describe to you the high precision measurement recently published in the Science Journal. This picture here is at the heart of this analysis. This is the drift chamber. You can see the beam pipe coming in through the center of the cylindrical detector, surrounding silicon sensors here, but then the main focus of the analysis will be on understanding the drift chamber. Surrounding that is the electromagnetic calorimeter and hadronic calorimeters, which are of course playing crucial role for the electron channel. But you will see that the emphasis on the analysis, because we are trying to measure a mass in a two-body decay, we want to measure the momenta of the particles coming out of the W decay, the electron or the muon, as precisely as possible. And that is done with a fundamental analysis, a fundamental understanding of the drift chamber. So with this, I'll say a few words of motivation, why W boson mass measurement is one of the precise measurements worth pursuing in particle physics. I'll describe the analysis strategy, say a few words about the experimental apparatus and how the data samples are collected. But most of the time will be spent on how the actual calibrations, how the constraints from the data are applied to make the calibrations as precise as possible. I mentioned at the bottom here is the link to the science paper. And I recommend that in addition to the main paper, which is only about 6 pages, there is about 60 pages of supplemental material that describe more of the details. In addition, I would say that many of the details are similar to the analysis published in 2012 with the corresponding PhysRev D long article in 2014. So if you read the supplemental paper here, many things which are the same are actually described in our 2014 long article, and there was another 2008 long article before that. So there's quite a bit of published material out there now about how the analysis was conducted over the last 20 years. Okay, so just a few words about MW. The standard model we now know is very tightly constrained. It has a lot of mathematical axioms and principles built into it, and there are some parameters in it as well. The parameters that are relevant to making the expectation value of MW are these. So Higgs mass, top mass, Z boson mass, the muon decay constant or extracted from the lifetime of the muon, the EM coupling run up to the mass of the Z, the relevant energy scale. So these are all quite precise now. So at tree level, one can get the expectation value for MW. This precision has been exceeded for a very long time. So, loop level calculations have been around. For example, before the top mass was discovered and before the Higgs was discovered, certainly, MW was one of the measurements that could be used to infer a value of M top by basically calculating this Feynman diagram and saying the difference from the tree level is due to this. One can then, once the top mass started becoming pretty precise, then one could play the same game with Higgs. So as Rishi mentioned, at that point, before 2012, you could play the same game, try to infer what M Higgs would be in order to make the calculations with these kind of loops compatible with the measured value of MW. So now we are going one step further. And so the similar motivation remains that if you know the calculations of all these quantum fluctuations precisely, then if there is any difference, one possible interpretation is there are some potential new particles in some loops like this, which might be contributing. So on that note, here is how the number from the standard model expectation now shows up. The 4 MeV here labeled as inputs. This is the one coming from the uncertainty due to M top, the uncertainty due to the running of alpha electromagnetic. Others are actually small component from mass of the Z boson, mass of the Higgs boson, and so forth. This other 4 MeV, in some fortunate sense, it is a similar contribution, is the calculations within the standard model, higher order loops. There are at some high order small QCD contributions that are difficult to calculate. So those things are all estimated to be about 4 MeV. Okay, so in the paper, we say a few words of introduction, really, a couple of paragraphs on ideas that have been around for some time about what new physics might exist beyond the standard model. And so we provide some references as to what some of these calculations might predict for additional contributions to MW through the kinds of calculations that we discussed earlier. So this just says if the MW comes out different or whatever it does, then one possible venue is to explore what we might be learning in terms of ideas like this. So I just picked one paper here, which is taking, in some sense, a small extension to the standard model. One more scalar is added, and it's the simplest possible scalar in some sense that you could add, which is that it has no standard model charges. So it interacts with the standard model particles because of the mixing with the Higgs, and the Higgs, of course, interacts then with the standard model particles. So this alpha here is the mixing angle. So in terms of mixing angle and hypothetical masses of this second scalar, what kind of MW contributions you could see. And so this was calculated. I'm sure there are many papers on this. And you can see you can get positive contributions and negative contributions, depending on the mass of the particle and so forth. Okay, so another favorite has been supersymmetry. There are huge exclusions from the LHC now in this space, but it's a large parameter space. So it's not so easy to say which part of the parameter space which is excluded can contribute how much, and which parameter space might still be surviving. And so maybe roughly tens of MeV contributions to MW might still be possible. Anyway, these are motivational arguments only. Coming to experimental status. So this was a time, 1998, roughly before the start of run 2. So it's a random snapshot. When Lab 2 experiments were making precise measurements of MW, most of the Tevatron measurements of MW were coming out just about this time from run 1, but run 2 had not yet started. So you will see later on, this ellipse is now significantly smaller after 24 years, both in the MW axis and in the MTOP axis. But this was sort of how we were looking back then in terms of precision physics in MW and top plane. Okay, this is one other parameterization. It's called the STU, which says whatever new physics is, if it happens to contribute through the boson propagators, so the WZ photon propagators, then there is a way to parameterize it in some generality. And so the 3 parameters are needed to capture the various contributions that might be there in those propagators. So typically U equals U is assumed. And so just to collapse it to 2 dimensions, it is often plotted in the ST plane. So this is the plot in the particle data group publication. And you can see the 2 sort of most constraining measurements in terms of precision physics is MW, and the other one are the Z-pole asymmetries. But it's also very interesting to see that in this parameterization, the 2 have different slopes. So it is more constraining to measure them both because the intersection is even more tightly constrained than any one-dimensional constraint you can get from either of the measurements. One last thing I would mention here, that this U parameter, which is generally thought to be, assumed to be 0 or small in comparison to S and T, MW has sort of the nice unique feature that it's the one that also allows you to put some constraint on U. So now let's move on to where, 2012, 2014, the previous CDF measurement. I just show you one table from that paper. The total uncertainty at that time was 19 MeV from all the CDF analysis that had been done up to then from run 2. And that was about 1/4 of the total data set. So this data set was taken up to 2007 or so, and the analysis was published in 2012. So I'll come back to this table, but for many years, every time a measurement was done, looking to the future, because we knew more data would be available, what would be the expectation from the analysis perspective that various calibrations or various uncertainties that were needed to be constrained better in order to make use of higher statistics, would those systematic uncertainties be reducible? So the thinking was, to the extent that you can understand the data precisely and use the data to constrain those systematic uncertainties, then hopefully they would be reducing with the statistics of the data. So that logic was felt to be applicable to the ones labeled in green. it was felt to be somewhat applicable to the ones labeled in black, but there were other issues associated with these particular issues that I'll come back to. And then there were others that really relied on completely external theoretical calculations like radiative corrections, or some combination of how collider data at the time from Tevatron, but also in the future from the LHC, and other measurements like Drelian, DIS, how those would proceed and how the combination of all those data would produce a consistent global fit, which would then be usable by the analysis. So not quite known how the red or the ones would improve. Tevatron itself would make some contribution here through the lepton charge asymmetry measurement, but it was understood that that was not constraining all the possible degrees of freedom that mattered for MW. It constrained an important one, but certainly not everything. So external input was going to be needed for the PDFs, as was well known. So we'll come back to this slide and compare how this analysis compares to where we were about 10 years ago. Okay, so one feature of the Tevatron that helps is that we have a proton-antiproton collider. So
sorry,
that means,
can I have a small question on the previous slide, please?
Yes, please.
Yeah, just to understand the color code, I mean, if I take the two red ones, so we'll say these are entirely like more theory oriented, and the rest are the green and the black. These are all experimental, right?
Almost right. The PTW also requires theoretical modeling. The argument is that the theoretical modeling is constrainable by the data.
Right, right. So I mean, okay.
Theory and experiment. Parton distribution functions is a combination mostly of experiment, but also of the global fitting methods that are used. So there are various global fitting.
I mean, for example, the lepton resolution, I would say it's purely experimental, like, you know, how yes. So like that way I was trying to. Okay, I got it. Thank you.
Yes, the green ones starting from the top are purely experimental. The black ones are essentially purely experimental. The ones that start going down become some kind of mix, and the radiative corrections at the bottom is purely theoretical.
So, sorry, a clarification here. The QED radiative corrections, do you mean the effects due to real photons emitted, collimated to the leptons?
Yes, and that's the largest effect by far. But then there are heavy boson virtual loops. There is a small effect from initial and final state interference effects.
Okay.
And depending on how you do the calculation, there is also FSR from the W boson itself.
Okay. So the real emissions, I understand that because it's a transverse mass fit uncertainties, right? This is where I thought like it's a kinematics driven. So
yes.
So loops, I didn't know that it could have a bigger effect, but I thought this is coming from the real emissions one, the ones that you're missing. Or
yes. Yes. So I'll leave it to my theory colleagues to explain better. But as you know, at any given order, the loops and the real emission have to be properly incorporated, right, in the calculation. So
yes.
when we looked at the codes, there were soft and virtual contributions and hard radiation contributions, and then there is a cutoff in the middle, so you get cancellation. And so depending on the accuracy of the calculation, if you vary the cutoff, then some incomplete cancellation between loops and real in the end affects the real. I mean, it's all a calculation, so you cannot completely just isolate the real part of the calculation or the loop part of the calculation. So
no, I understand.
Yeah. So in that sense, yeah. Ultimately, experimentally, we only care about the real. But since the real is calculated from a calculation that has to include the loops, then, yeah, I think you know what I mean. Okay, so this aspect of the Tevatron helps in the sense that about 80% of the production at the Tevatron is from a quark, which is a valence quark in the proton, or an antiquark, which is again a valence quark in the antiproton. So given this presence to a large extent of a valence quark or antiquark, the PDF uncertainty is a little easier to control, shall we say, because the valence quark parton distribution functions are somewhat better known. And secondly, the range of X values, the partonic X values, is also at the level of 0.04. So the lower one goes there, the more you're exciting the quark-antiquark C in the protons, antiprotons. So the fact that we are not going as low also helps a little bit. So in addition to the sort of Born level diagram, W decaying to a two-body decay, there is a lot of initial state radiation, just depicted here as a single gluons, but of course there is gluon-induced production as well, where you get a QQ bar pair. So this could be a quark, antiquark. So there is a lot of soft radiation of all kinds. This shower is here. In the experiment, if you look in the picture on the right, for the W bosons, we are selecting I'll mention this again, that the selected particles are the ones where you want the Jacobian edge to be rather sharp or as sharp as possible. And those are the ones where the boson does not have much of a transverse boost. So you want to select events where this, whatever initial state radiation there is not as large or is not very large, so that the transverse boost does not contribute a significant amount to the momentum of the lepton. Because if it did, then you're trying to infer the relationship between the lepton momentum and the mass. And so if there is an additional contribution from the boost, then you become more sensitive to how well you either calculate the boost or how well you measure the boost. So for those reasons, we will be focusing on the soft hadronic activity in the calorimeter. So lots and lots of pions and kaons are getting split off here. So this activity is typically soft. So you have to calibrate that also though, because that goes part of the kinematic calculation. So this is roughly the level of calibration that is achieved on the hadronic activity. Much more directly estimatable is what would be the accuracy needed on the lepton to get a corresponding accuracy on MW. And that is just a simple transfer. So whatever you achieve there, it's the minimum that your MW precision will be. There will be other effects, of course. So what you will see is lepton calibration precision achieved of 0.004%, and hadronic sort of depends how you define it. It's a complicated beast spread out all over. 0.2% is sort of a metric. Okay, let's move on. A slice of the CDF detector, a typical cylindrical collider detector. So this is one quadrant. There's a mirror image on the other side. Here is the chamber I mentioned, central GIF chamber. It's called Central Open Cell Tracker, COT, about 1.3 meters in radius, starting at 40 centimeters or so. So the momentum calibration for electron and muon tracks comes from this. Then it is transferred to the central EM calorimeter, which is then used for measuring the electron energy. And the reason is the electrons are radiating, but most of the photons are captured within the cluster, there's small angle radiation. So event by event, the precision of the EM calorimeter measurement of the electrons is far superior to the event by event measurement for electrons in the drift chamber. So you go to the high precision method, but then you have to calibrate it. The hadronic calorimeters are central forward and the forward EM calorimeter as well. This is catching all the soft hadronic activity. And then what is not shown is the muon detectors, which are outside. So they're tagging the muons. Same kind of picture. This is the beginning of run 2. The silicon detector is being installed. And you can see that roughly 1.3 meter radius drift chamber. The EM calorimeter is hidden in there. And then this is the hadronic calorimeter. And the muon chambers, for example, are outside. Okay. So I mentioned event selection criteria. Keep the selection as simple as possible so that you can minimize the chances of any selection bias. For example, if the identification of the lepton were to depend on the topology of the hadronic activity, which direction the hadronic activity is going and is that spoiling the selection, then you get some kinematic correlation, which you then have to measure. So as loose as possible identification requirements, so some optimization was done. At the same time, you want small backgrounds so that you don't have to think too much about those. And at the same time, you want to maximize the information content in the W boson events that you select. And so this last point here says some trade-off between statistical power and keeping the events with a sharp Jacobian edge in the experimental value, measured value of this hadronic momentum. So the total momentum of the hadronic activity in the detector, that total momentum is required to be less than 15 GeV as measured. To sort of judge what happens, here are the event statistics one gets from the full approximately 9 inverse femtobarns of data collected over 9 years. Roughly speaking, the two channels, electron and muon, are about 2 million W bosons each. The fiduciality requirements on electrons are stricter. This is really just because of the construction of the EM calorimeter in CDF, built out of wedges. But between the lead scintillator calorimeters, those wedge regions are not so well instrumented. So one has to stay away from those, those edges. There are 24 such edges. So that kicks, cuts into the electron channel statistics. And particularly for Z bosons, it cuts into quite a bit because you are requiring that requirement on 2 electrons. So all this pattern here is essentially just the result of the fiduciality requirements and the acceptance effects it does on 1 lepton versus 2 lepton and which lepton it is. Okay. I mentioned misidentification backgrounds. We'll come back to this in the end, but approximately 0.5% background typically in each channel from misidentification. There is one large background which is in the muon channel when one of the muons from the Z boson goes in the forward direction. So roughly rapidity of 1.1 and beyond. Then the drift chamber, the tracking drift chamber, is not able to catch those muons. So that background has some efficiency related dependence. Mostly it's a geometrical acceptance dependence. So that was done carefully in a couple of different ways. And so that got pinned down.
Sorry, just a quick clarification. What you said, the fiduciality requirement for the electron case, did I understand correctly? This is a transition region between the barrel and the end cap. You don't consider that, or did I get it wrong?
The end cap doesn't matter because we are not using electrons in the end cap. So the transition region between central and forward is not the relevant one.
So do you consider only in the barrel region both electrons? I mean, yes. Like in your jet decay, like jet going to 2 electron particularly, that's what I was thinking about, not right. So you consider only the barrel region. Okay, great, thanks.
Yes. So the fiduciality that hits the electron acceptance hard is the fiduciality in the azimuthal direction between the wedges of the calorimeter. Okay, so the calorimeter has 24 wedges. So some fraction of every phi sector has to be removed because the scintillator response in that, what we call the barrel crack regions, is certainly not good at all for this kind of precision. And that then kills electrons.
Got it. It's not the eta one, of course, it's more on the pi side, but you only on the eta side, you consider only the central part. Yeah, okay, yes, that's clear. Yes. It's
more in the azimuthal region than in the eta region, exactly. Okay, so in general, what we have tried to do is start with the highest precision checks or built-in constraints that we can have. And the goals are, if you do that, you try to make your analysis as robust as possible by, for example, measuring the momentum calibration in multiple different ways, see if you get the same answer, which then leads to goal number 2, which is for the most important parameters that you have to measure in the experiment. If you do measure the same quantity multiple ways and you obtain consistency, then you can combine those and get higher precision for the final answer. So two sort of follows from one if one is able to work out. And third, try to minimize whatever to the best possible ability biases in the final answers. And one thing we have pursued in that context, there were some other things as well, is can we independently measure the mass of MZ, the mass of the Z boson, so that we get a constraint on how well we've calibrated the calorimeter and how well we've calibrated the drift chamber by not first using MZ as an input, but try to do it other ways and then use MZ as a check. And if the check works out, then it becomes an additional constraint. Okay? So for that, to pursue that philosophy, we blinded not only the measurement of MW, but separately also blinded the measurement of MZ. So let's say,
get clarification. So when you say the third point, should I think in this way? Like, for example, you are not using the electrons from Z decays to calibrate your electron energy, for example. Rather, you calibrate by a different source, and then you measure your Z mass and to check whether that fits well. Is that the philosophy? I mean,
yes.
Ideally, I would think that you can take the Z as a standard candle and get your calibration for electrons right. But you don't want to do that.
We don't want to do that from the very beginning.
Okay.
So the way you started your point is exactly right.
Okay.
You want to calibrate in other ways and then see if the Z boson mass comes out right. Yeah? That's how you started, right? And that's right. That's how we did it.
Got it. Thanks.
Yeah. Okay. So let's start with the calibration of the drift chamber. So here's a quick summary. Drift chamber calibration, then momentum calibration for muons, then see if the mass of the Z boson is coming out correct, unblinded on one day. Then use the electrons from the Ws as a sort of a test beam source in situ. But this is, of course, independent of the energy of the electron. This is just trying to see if the energy of the electron in the calorimeter compared to the momentum in the tracker, which is calibrated, use that as a calibration source. So this is a line, so to speak. It's broad because of radiation, but there's a peak here. So this calibration method then transfers from tracker calibration to EM calorimeter, which is then checked or confirmed with the Z mass, as you said, in the electron channel. Then I'll say a few words about resolution. This is relatively very well constrained and small systematic. Then, as much time allows, we can go into hadronic recoil modeling. And you'll see in comparison to this, which is as much as possible based on first principles, hadronic recoil calibration, because it is such a diffuse object with all kinds of complicated things going on, it is much more of a parametric modeling compared to here. Okay, so let's start with the drift chamber. So this is a slice of the drift chamber from looking at the side. So this is the end plate, a thick aluminum plate on one side of the cylinder. And the slots cut into it are where the drift chamber wires are inserted. So there are 12 wires in every slot. And so when a charged particle comes through, it is traversing 96 wires, and the efficiency is very, very high. So the number of hits we are getting on a typical trajectory is quite high, a big fraction of the 96. Okay, so this method to align the drift chamber was the first thing you have to do. Other experiments have used it also. We have a rain sort of coming down from the sky of cosmic rays. And these cosmic rays are being collected during collider operations, of course, because for the trigger, they look like muons. So the muon trigger is able to pick them up. And even when beam is running, you will get cosmic rays within your, embedded within your events. You can also then look for situations where the proton-antiproton bunch doesn't actually have a collision. So some fraction of the events are looking like this, where the hit confusion and all of that is really just not there because the event is a completely clean cosmic ray triggered event. So you can average the plus and the minus cosmic rays appropriately so that on average your tracks have zero curvature. So you really can sort of make straight lines cutting through your drift chamber. And we developed a special tracking algorithm, which instead of just propagating the track from the beam outwards, it's able to track the complete trajectory. One side is inward and one side is outward. So a long, up to 192 hit reference line, in a sense, this tracking algorithm can make. And then with respect to that line, you can align all the cells to pretty high precision. And certain deformation modes of the drift chamber, which collider tracking is somewhat sensitive to, because it will change the track parameter, but it will not tell you in the residuals that you have a bias here. So that bias gets absorbed into the track parameter, which is what you want to avoid. Some of those deformations are actually visible in this particular kind of track, which is a single track on both sides. So that is able to eliminate many deformation modes quite well. Not every single one of them, but there's a complementarity between what type of deformations can this method eliminate and what kind of deformations can you then eliminate from collider tracks in a second pass. So we have a two-pass tracking calibration here for the drift chamber, which is first from cosmic rays and then collider tracks. So there's a dedicated paper on this. I will just flash 2 or 3 plots from it, taking one particular layer of the drift chamber, the innermost, for example, here. The numbers on the x-axis are related to the azimuthal angle. So this is just the entire 2 pi azimuthal angle unfolded. The a priori alignment that goes into reconstruction before this process is done is based on survey measurements. So one can see the survey measurements have an intrinsic precision of 50 microns or something. This is collapsed down to 1 micron given the power of this particular cosmic ray alignment method. And you can see that the flux of the cosmic rays is sort of extending fairly uniformly, not exactly, more vertical than horizontal, but there is quite a bit of pretty horizontal cosmic rays coming as well. So you can get pretty good precision pretty much all the way across the azimuth of the drift chamber. You can see here where this point and this point at the end corresponds to exactly the horizontal direction. There, the statistical precision is somewhat worse compared to the other directions, which are more vertical, where the statistical precision is higher. But even here, even in the region where the cosmic ray flux is the smallest, the statistical precision is quite good. So I would mention here that this whole alignment process has been done 3 times. It was done every time there was a publication of MW following, so somewhere around 2004 and 2009 and 2013-14. And every time, not only get some more cosmic rays, but the technicalities of internal biases and whether the analysis itself is closing up on itself, and are you getting consistent answers if you look at it different ways. This kind of closure has steadily been getting better. There were non-closure issues from 2008 or so, which limited this number to maybe 4 microns or so. So now there is much more closure here, so the precision actually improves. Here is one example of closure, which is you can now break up the track back into its 2 parts, the top half and the bottom half, and you can then compare the tracking parameters separately from those 2 halves after you've done the previous alignment. So it's a sanity check that is there closure here, and to the extent that the histograms have 0 mean and a pretty nice Gaussian shape, you are more confident now that there is closure. So these are just some indications. There are many plots in that paper. The first 5 plots here are spatial coordinates, the 5 spatial coordinates of a helix, and the last one is a timing coordinate. So the cosmic rays are coming at random times. So the drift chamber, you can also measure the time. And so there is closure in the timing measurement from the top half and the bottom half as well. Those quantities can then be split up into polar angle, azimuthal angle, and see that it's not just working on average, but it is working uniformly across as many ways as you can slice the drift chamber. And this is the variation before alignment. The open circles are the residual little variation after alignment. In the paper, we have zoomed version of these points, so you can see is there any, to the extent the cosmics are sensitive to some biases, can we see any remaining biases? So the conclusion was no. Then we can try the collider tracks, and there are some weakly, what we call weakly constrained modes. So some kinds of deformation where the cosmic ray track itself would be deformed, or its parameters would change, but the only thing we know is the residuals from the track to the individual cells. And if the residual pattern cannot follows the mode of deformation, then it's invisible to you. So from that perspective, there is a weak mode which is important, which can be constrained quite nicely from the collider tracks. This is taking the energy of the calorimeter divided by the track momentum. And if any bias in the tracker is dependent on charge, since it's measuring curvature, it will show up as a difference between positrons and electrons. So there is one important parameter that is the most important parameter at high momentum. This is called the false curvature. So you literally have a twisting effect going on in the drift chamber, and so that makes one charge go to higher momentum and one go to lower. And this is a bigger and bigger effect as the energy or the momentum increases. So we will be arguing that based on the alignment, we believe that the curvature that is measured in the tracker is just a simple polynomial Taylor expansion, basically analytic function of the true curvature. So Q over PT is the true curvature you're trying to extract. This is the quantity you measure. So there is an analytic relationship between the true track that comes in and the measured track that you get out. So the C0 is the false curvature term. It's the one that as PT goes to infinity, then these terms will become smaller and smaller. And C1 will become 1, sorry. These ought to disappear. And this is the false curvature, which could eventually take over your measurement at infinite momentum. So this is an in situ calibration of that. And it was done as a function of polar angle and azimuth and so forth. So here is the one that sort of physically matters the most, which is the polar angle dependence, positrons minus electrons. After the alignment, there was a small bias here, and it is not unexpected because it is a weakly constrained mode in some sense from the cosmic rays. There's a particular way it can happen where the cosmic rays deform and you can't see this. So this was eliminated, and I say 0 here because the number of decimal places you would put to make any significant effect on any of our particles is really, really small. So we think we have eliminated the C0 term. Now what remains is to constrain C1, C2, and so forth, and this we would call the calibration of the tracker. Before going there, I'll say a few words about, I'm going to speed up a little. We'll say a few words about the overall line shape fitting. How is any of this analysis done for the collider data? In general, the idea is you make any distribution of any kinematic quantity, invariant mass or transverse momentum of the lepton, anything that is sensitive to a quantity you care about. And you then have to generate calculated line shapes, including every scale effect, resolution effect, nonlinearity effect, physics effect. All that has to be calculated. So there is a customized simulation developed over a long time that keeps getting better that will do these calculations. And then you have to, the parameters of this would be things like the energy scale or momentum scale or some nonlinearity or radiation or physics, everything is in here. So for example, here is a transverse mass distribution. I mentioned earlier the Jacobian edge. So here is the edge, which is roughly at half the momentum, half the mass of the MW shows up as the PT of the lepton if the decay angle is 90 degrees. So that's what we mean by Jacobian edge. When the decay angle is less than 90 degrees, you start populating this region because the PT is smaller, even though the energy is there. So we are measuring PP. This is a PT dependent quantity, and you can see the Jacobian edge moving. So there's been plenty of discussion of the generator model. So I'll quickly describe the generator model, and we'll sort of get back to this if we have time. The calculation that has been used for a long time, both CDF and D0 have used it, is ResBos. This has also evolved. We are using the version of ResBos that was used also for the previous analysis. I'll say here, we've thought about updates. We can come back to this point. This calculation is doing the QCD part of the production model, initial state radiation and so forth. It has the ability to do resummation and interface to some fixed order, so forth. Then the W boson decay, so ResBos gives the leptons. Then you have to interface some other radiative, QED radiative calculation. So this is done by Photos. Photos has a mode in which you can sort of interface it to some other program that does the other part. So this combination of ResBos and Photos is our baseline. I'll quickly say that the Photos part was checked against a program which is more inclusive. It also has multi-photon radiation. It has one photon radiation, which is exact to order alpha. It has interference effects. It sort of does more things. So this paper discusses both qualitative comparisons, such as energy of the photon, number of photons, many things you can plot, just to see qualitatively are they similar. But then quantitatively, you can generate events with one calculation and fit the other or vice versa. So you can cross-calibrate the programs by generating pseudo data and just seeing if you did it one way or the other, how would the difference be? So this is a pure Monte Carlo study you can do to cross-calibrate one versus the other. So pretty good cross-calibration showed up. So overall systematic uncertainty from this is you think about 3 MeV. Lots of thinking into various issues associated with the QED or electroweak aspect of the radiation part. Okay, so now we go constraining the parts of the theory model. And so this is, the questions comes up, how sensitive are you to the assumption you make about the theory modeling that goes in? So our attempt is to constrain that as much as possible with collider data. So here is the constraint from the PT spectrum of the Z boson. And when this game started long ago, it used to be a 1-parameter fit. At some point, we moved to a 2-parameter fit. 1 parameter constraining the low part of the spectrum and 1 parameter constraining the high end of the spectrum, which is more the regime of fixed order calculation. Somewhere here is the resummation region. Somewhere down here is the non-perturbative physics. So we found so far that 2-parameter tuning is working pretty well. So you can see the quality of the fit in the 2 channels. And I'll come back to this again with the W boson spectra as well. So these are just the Z boson spectra so far.
One quick question, Ashutosh.
Yes?
Yeah, so what are the pattern distributions you have used here in this fitting?
This is NNPDF.
Are those LHC constant PDF?
Are those, sorry?
LHC constraint PDF?
Yes.
Okay.
Yes. So these PDFs are always evolving. I don't remember exactly when NNPDF was published. NNPDF 3.1 to be specific.
Okay.
So I'm missing the date of publication, but certainly a lot of LHC data are included.
Okay.
And more Drelian data and DIS data from other places. So we are trying to use the latest PDF, but it can't be yesterday's PDF because all of this has to be decided a few years ago. Okay, so at least one aspect is of the theory modeling is constrained this way. This was a distribution we didn't look at in the past, but it has been used by our colleagues on other experiments. So this is the angle, azimuthal angle, so to speak, between the 2 leptons. So this is a measure of the PT of the leptons, but done in a different experimental way. So this time we use this distribution also. All right, so let's go to the momentum scale determination now. The calculation, as you can imagine, you have to, every physics process that a particle goes through encounters multiple scattering, energy loss calculations, all of these things. Our previous papers have published all the equations that we used. So this particular paper doesn't repeat every one of those because it would just be a copy from our past paper. So we just reference the past papers. But just to illustrate what that really means is one puts in a detailed 3-dimensional material distribution map. So this was done for our full CDF simulation as well. So it's a giant input, so to speak. And the granularity of the mapping of the silicon and aluminum, solder, how much there is some gold here, this, that. All of that, people did a lot of careful work to weigh all of those things and try to make this input to GEANT as accurate as possible. So this same input is used here, and effectively we are doing what GEANT would do, that you would track the particles coming through these small volumes, which are a few millimeters on the side. And then as they come through, you basically implement the processes according to those physics equations. So all that detail is in our 2014 paper, and some of it is also in the 2007 paper. So you track these things and then you just propagate them, all first principles. Okay, I should move on. This is one of those layers. I showed you the azimuthal view. It can also be unrolled into layers upon layers, like cylinders inside of cylinders. So this is longitudinal versus azimuth. This is one of those cylinders, just to give you some idea of the granularity that this map has. It's standard input to GEONT. Okay. Now we can use resonances starting with J size and epsilons. So J size statistics, and this time even epsilon statistics, are sufficiently high that you can, instead of just doing inclusive fits, you can start binning them into the important quantity for the tracker. So the important quantity for the tracker is 1 over PT, it's the curvature. So we can average the curvature of the two muons and make sort of the average curvature axis here. And every one of these bins is coming from a mass measurement of the J psi, which independently, the world average is extremely precisely measured. So here is the red is the template from the simulation, and the blue are the data. So that color scheme will be followed throughout. So every one such fit, this is, I think, the 8th bin, so you can count somewhere here. There is one such fit for all of these. And we are arguing that based on analytic calculations, we know what the C1 parameter would be from that analytic expression. We know what the C2 parameter would be due to. We don't know what number it would be, but we know what would cause it. One thing that causes the C2 parameter is if the energy loss calculation is slightly wrong. So we think our equations are correct. So the map itself in which the amount of material is encoded could be slightly off. It was done by weighing and a lot of engineering knowledge. What we are saying is a 2.6% change on the proportional change, not absolute, but a 2.6% proportional change on the amount of radiative material, on the amount of ionizing material. That is what is required to make the C2 term go to 0. So when the C2 goes to 0 in this plot, it becomes a horizontal line. So because C0 is 0 and C2 is now 0, we expect this line to be exactly flat. And it's difficult for us to sort of do any ad hoc, polynomial random fits here, because we just can't motivate those. So this is what we see. You see the points, how they scatter around. There has been discussion about a few points over there. There's been discussion about this one point over here. And we played around quite a bit to see anything reasonable that was still allowed by all the constraints we had already built in. At some point, we decide that we don't want to chase warts in the data, funny points show up here or there. So we stick to our analytic fit and extract a momentum scale from this. Okay. We can then try that on the epsilons, or we can do the epsilon independently. And one important thing there is there are two ways of tracking. We use one of them for the high momentum particles. For the J size, we use the other. The epsilons are acting like a bridge. When you apply the beam spot as an additional constraint in the tracking, in principle, you know the beam spot exactly, which we do. You should be able to apply it as an additional constraint. But if you don't or you do, you should get the same answer if there is no bias of some kind of deformation or something. This was an issue in our previous analysis. It was an action item to figure out what was causing that discrepancy in the past. And we have published exactly what we found, the source of the discrepancy. Okay. So those two are now consistent. So this is the table of momentum scale systematics. I mentioned that this is all done in parts per million now. So many things got better. The calculation of radiative corrections in the J size epsilons got better. So you can see many small numbers. And it's somewhat gratifying to see that the world average mass measurement of the epsilons is actually the largest contribution in the epsilon systematics. So we need to know this number, and that's the largest. Yeah. J size are much more precise than that. So J size world average is essentially 0 error. All right. So we talked about this earlier. Z boson mass as a check, not used as an input initially, just to see whether everything works out or not. So you can see the consistency that. So this was a blinded measurement like the W's, and you can see the level of consistency that worked out. So in fact, less than 1 sigma agreement. Okay. At this point, we go to the precision logic and we say, this has been used as a standard candle. So given this precision, we can also include this as one more calibration point. Until now, it was not, but finally we can add it as another calibration point. So it helps to improve your precision a little further. So now this is the plot with the epsilon included and the J size you saw earlier and the Z mass point included. Okay. So all the solid points are the ones which are measurements. This is the final answer coming from the combination of all the measurements, the open cross. So the open cross is the one that we now want to apply to the leptons from the Ws. Okay. So the Z is slightly on the other side of the W in 1/PT, and these points are all on this side.
Sorry, I probably misunderstood. So the when you measured using the previous calibrated, let's say, muons, the Z mass. So if you go back to the earlier slide, so this is what your result was, right? Using previously low energy calibrated, muons, right?
Yes.
So now, and this is what you found MZ to be. But when you say that I calibrate now using Z data, do you mean using this MZ value or using, for example, PDG best fitted value and their errors?
Let me explain the following way. This measurement, 91,192, relative to the PDG value of 91,198, that ratio leads to this point in the calibration. So you see the green point?
Yes.
The green point is the calibration you would get from the Z bosons.
Okay.
Now you can average the green point with the blue points and the red point.
Okay, I see. Okay, now understand. Yeah.
And you can see that is leading to the precision of the cross. So the cross is the average of the green, the blue, and the red.
Okay, and just want to make sure what exactly is the what determining the size of your 1 sigma error?
In which point?
In the green point.
In the green point. The green point is using this statistical error. And so it's a good question because it depends on what you want to show in that plot versus what you want to use for the average.
Yes.
Yes. What you want to use in the average is the 6.4, certainly. You do not want to use the 2.3 because this is an independent calibration from this. So the 2.3 is not included.
Okay.
Okay.
Right. Sounds good. Thanks.
Yeah, the alignment is included because it doesn't go into the Z in the Ws that is the same way. So the alignment has to be included. The QED is not included to a large extent because most of the 3.1 QED in MZ is the same as in MW. So this part will cancel mostly when you use the Z alone. So the 6.4 is included and the alignment is included. The two numbers in the middle are not included. That's the blue point as an independent calibration. Sorry, that's the green point independent as a calibration source from the blue.
Got it. Thanks.
Then you can combine the green and blue. Okay, so let me see. I may have to speed up. Next aspect, again, trying to do as much fundamentally as one can. Our calorimeter is lead scintillator. So we spend some time trying to get the precise thicknesses, amount of scintillator, some dead material here or there, all these things. And a separate giant geometry was built with the as constructed parameters, as much as information as we could put in, so that we could extract what the properties of the showering would be, low energy response, high energy response, leakage, nonlinearity, shower, everything. So try to get whatever we can get out of GEON, but then there are always some little pieces that you don't know. You may not know the exact thickness. You may not know some slight amount of dead material somewhere, this or that. So then you can take the GEON input, make it part of your custom simulation. So that paper describes how the giant was parametrized so that it can be done very quickly. This line shape is now calorimeter energy to track momentum. And the three regions here are this region where track momentum is low is the radiative electrons. So you have to make a small correction again to a a priori giant input, which is the amount of radiation lengths in the experiment. And it is about 5% off. So we have to make a 5%, proportional 5%, not absolute 5% radiation length, of course, that would be huge. 5% to the nominal amount fractionally to get this tail to match exactly. The calorimeter thickness, about 19 radiation lengths. We had to make sort of a 0.1 radiation length tweak to that so that this part of the tail would come out right. Both of these then give you an ability to get this line shape, which is the important one, correct, which is the peak. And now you can understand from the peak what the energy calibration of the calorimeter is. So we try to do it as first principles as possible. Then we see what happens to the Z mass if you use this calibration. Okay. Let me skip this. This is just the same fit describing how the tail was fit for. More plots looking at nonlinearity. So you can get the electrons bend in momentum or transverse energy bends because it's a showering calorimeter. So it can always have some small residual nonlinearity, which the giant model doesn't have. Scintillator aging effects, all those kinds of things, experimental things. So a logarithmic shape is assumed here, and then you make this beta adjusted so that within statistics you get flat calibrations. So each of these points is one of those line shape fits, but bend in this quantity. Spatial uniformity, good spatial uniformity. So now we go to energy of the electrons calibration check. And this is the Z mass that was again blinded, which again becomes, like you asked earlier, an independent source of calibration, ultimately. So this time it will be the track versus calorimeter calibration we just talked about. This 91194 relative to 91198 is another independent. And again, here you can say which of these systematics should be included in the calibration, which not, and similar logic. The ones that you think ought to cancel directly in the W, you don't include in this calibration. So all those little correlations have to be taken into account. Okay, I'm just going to flash some additional checks with the Z's, which steadily shrink in precision because you are doing more and more with the Z sample different ways. You can split them up into radiative and non-radiative electrons, one from the tail and one from the peak. One particular shape I flashed. This is binning into those three categories, both non-radiative, both radiative, one of each. You can use the calorimeter cluster, just calibrated directly. Now that's the high precision, as high as you can get. You can try to use the tracks directly, which are very radiative. So you can see the precision of the checking gets weaker and weaker. So we stop here, but something we can do. So okay, I'm going to skip resolution details. If time allows, we can come back to this. Basically, all those peaks we saw, every time you're trying to use it as a calibration source, you also can see the width of the distribution and the relatively narrow peaks. So the peaks are the peaks are narrow. So the width is very well constrained with whatever you think is the source of the width. And so the systematic uncertainties are small as well. All right. I may have to go relatively quickly on this. We are now trying to calibrate the hadronic activity. So the basic idea is muon momentum or electron momentum balancing against all the rest. So the fundamental assumption here is the Z boson events do not have any true intrinsic high momentum neutrinos or something that really carry away missing momentum. So there should be balance within the resolution of hadronic recoil measurements. There is a small but important effect here, which is the muons and electrons are themselves depositing energy in the calorimeters. Those have to be explicitly excluded from all this. These are separately measured. This is separate measurement. You can't do double counting. So the next few slides are talking about how the double counting is eliminated. You will see in the calorimeter, this is the calorimeter towers. electron energy deposition, large amount, some muon energy deposition, and this has to be excluded from the calorimeter quantity that you are calculating. So that exclusion effect is important, and it has to be calibrated as well. This is plotting just how that excluded energy is varying with the topology of the event. So there is a semi-empirical model here which tries to capture that, and then you can use the distributions from data to constrain it. So this is a data constraint on which the simulation is tuned. Okay, now we can do the rest of the hadronic calorimeter. Let me flash forward. You will see these axes. What we call the eta axis is the boost axis in the Z case, because you have both leptons, so you can calculate this axis. This is the perpendicular axis. For W's, you only get one lepton. So there is a lepton parallel axis and a lepton perpendicular axis. So projections of all the quantities you are wanting to study on the two axes respectively is what one plots. So now I'll flash, I want you to see sort of the level of agreement on the tuning plots and the level of agreement on other plots which are not used for tuning. So we can see how predictive is the model in some cases. This is the balance amount. So calibration says you should be able to balance it and come close to zero. You should be able to then look at the width of the balance, which is a resolution measure. And as you starts to get some jets or something, the resolution goes up. This is GV. So there is a model for this. There is an additional effect perpendicular where there is some two-jet activity. So it's a broad topology event where the resolution gets worse because of widening in the other direction. So there is a model for that. There is a model for the angle resolution. So the angle between the boost of the Z boson in this case and the other activity, which is sort of back-to-back. But because of all low energy fluctuations and some particles never reaching the calorimeter and all of this, this angular resolution is poor when the PT is small. So this is a low PT plot at the top. You can see very wide smearing. This is one of the higher PT regions, and you can see some collimation happening. So this activity is becoming a little more collimated with better resolution as the PT is increasing. You can see that here. Okay. Now I'll flash even more distributions. All I want to emphasize is the level of scrutiny we are looking at every time we say new on the slide. This is more distributions that were not examined in the past. We are also examining them in a, looking at the various 4 moments of the distribution, looking at shape comparisons and so on, to try to see that we are not just looking at averages or something, but also trying to match actual shapes of resolution functions and so forth. So with that, I'm flashing just a few plots from the paper. We can go back if time allows. So these are not inputs to tuning. This is important contribution, important components now for the W's. So we are switching to W's to check. This is the energy in the hadronic recoil parallel to the lepton, perpendicular to the lepton. So 2 components. Only statistical errors used. Correlations are too complicated to put into the chi-square. So these are only statistical chi-squares, but reasonable, and all the moments matching up reasonably well. One more new thing. So we talked about the boson PT constraint from the Z's. So this is one more aspect, which is calculation also has to get the WPT right. In the past, we just used the theory to say the theory will convert the PT of the Z to the PT of the W. So this time we added the data from the W's directly. After all this measurement procedure was done, used a completely independent calculation to extract how that ratio would change for higher order corrections, which can be parameterized in some way by scale variation or something. So the second calculation was an attempt to say, let's see what this ratio would depend on, make some variation from there, put that as a correction or a tuning or something like this, and then include a second tuning based on the WPT spectrum, including the correlations with everything else we just talked about. So you could do a lot of things and separate out the effect of one versus the other and sort of extract a full constraint from all the correlated effects combined. So having done all of that, you now get an additional constraint. And at least from this analysis, we got confidence in the response because it was not requiring any additional tuning. So this ratio became a way to capture the precision improvement we could get from it, but no central value adjustment had to be made. So for what it's worth, with some adjustment, the ZPT comes out looking nicely, and with no further adjustment, the WPT also came out looking at just nice with the response version that we had. Okay, we are really running over. Maybe we can come back to discussions of PDFs. I'll say a few summary words here. How an NPDF was used. Other PDFs was used as checking. Differences came out within the precision of an NPDF itself. So wouldn't matter which of those we used within that precision, roughly the same answer. We also tried NLO PDFs just to see what would happen there. We tried estimating higher order effects from scale variations and so forth. And looks like the data constraint is the important one. Sort of the theoretical issues within PDF fitting appear to be quite small now. This is where we are. And there are 5 background processes. Maybe I'll leave this to discussion if you have time. I will simply flash the table of backgrounds. You can see quite often small effects. Certain fits are more sensitive than others, and we understand the reasoning behind that. This is the one large background, but we did it 2 different ways to get the normalization and the shape of the distributions that matter, and pretty good consistency there. Okay, so blinding, the random offset of some size was chosen. This was kept the same as the 2012 paper. We thought, why not keep the things that are the same, accepted, published, we left them the same. Okay, so now I can simply flash and wrap up. Flash the muon PT spectra, muon electron transverse mass spectra. It will always be blue are the data, red simulation, and this is the difference. This is the residual of data versus simulation. And we couldn't see any systematic trends, some random points jumping. Lepton PT spectrum. The one that's most sensitive to all kinds of systematics is the neutrino PT spectrum. And then we can fit all of those because they're all calculated, predicted, and should be. So here are the separate numbers for each of those. So you can quickly scan how different they are or how similar they are. Then since every correlation to all parameters is known, one can make a big correlation matrix standard method and do whatever combination you like of all 6 subsamples of the 6. So this was done in the past. So we were asked to do some more. Pick 2 out of 4, 6 to 4 out of 6. You can do whichever combinations you like. So I guess I would quickly mention the column at the right. These are the statistical chi-squares of whichever inputs you are combining. So it's taking that covariance matrix and just converting that into a chi-square measure. Okay, so we can flash forward. This table we already spent enough time on, so we can compare to the current table. This is only the transverse mass fit. So you can see where there was improvement sort of with statistics. In some cases, less than that, because we know some things couldn't be improved. In some cases, we were using substantially more information this time. In hindsight, we could have used it last time. We just didn't think about it. So in some cases, we did better than statistics and so on. Okay, so let's see this more detailed tables. I think I'm just flashing things from the paper, the combined fit individual contributions. Okay, we should. Everybody has seen this plot. This is figure 1. This is figure 5. And this is the one thing, just the timing worked out this way. We were wondering how to include LHCb. It was not published at the time the paper was sent out. And at some point we got acceptance from the journal editor and reviewers. And then the paper went into some kind of frozen state. LHCb was published after that. So we are finding some way to do this. But in the meantime, all the slides, when we show this plot, we will explicitly acknowledge LHCb was published earlier this year. And some discussions are actually happening how we can change the plot. But here it is. So a lot of discussion has been, we can come back to this, but this is where, how everybody else, here is D0 atlas. Anyway, it's a plot of independent measurements. Okay, many improvements were made. I should wrap up. So if you have time, we can come back to improvements made and their effects and so forth. Okay, here is our answer, 8433.5, 9.4 MeV, about a factor of 2 improvement in precision from the last one. The statistics helps, of course, factor of 4 in statistics, but the commensurate improvements in analysis, some of them were important to get this because we had some limiting issues from the last time. And as you can imagine, those were important to tackle. Otherwise, you wouldn't be able to exploit the data in this way. So the last 2 statements, I just leave you, and these were how the paper ends. And again, thank you for staying a little longer. Actually, I'm over. So let me stop here and thank you for your attention and this opportunity.
Thanks. Okay, so there are questions. I think go ahead. I can't see whose hand is up. Govinda.
Yeah. Ashutosh, I have 2 questions about this correlation. Mate distributions, electron and muon channel, are they correlated or uncorrelated?
Let me flash, for example, this table. So we can go line by line. You can see the last column. Every time there is a last column which shows the correlation. Some things are measured completely independently. You can sort of imagine efficiency of electrons and efficiency of muons, not correlated.
Okay.
Hadronic activity was done in a combination of both channels. So all the Z boson events are combined. There is no reason to think that the electron and muon channel is sampling the hadronic activity differently. Physically sort of impossible. So we do that combined, and so it's completely correlated.
Okay, so that I understood. And let's say another small point is a lepton distribution, PT lepton distribution, and a PT nu distribution. How they are correlated? That is also correlation.
That is also correlation. Yes. It is difficult to show how to show that. Yes, they are also correlated. So the way it's done is in the covariance matrix, you have for every one of the 3 fits or every one of the 3 channels, 2 channels, there is a parameter that says which way the lepton energy scale or resolution or anything, which way is the fit going to move. So there is a signed derivative for every component, for each channel, for each fit. So it becomes a 6-dimensional covariance matrix from every source. So you have...
No, actually I wanted to see the simple, if you have the covariance matrix, if I want to see, that was the good for me, for not only few channel, in other channels, you can get that one somehow.
Yeah, there is an enormous covariance matrix. Yes. The number of lines it has is huge.
Okay, that's the one thing. And let's say that if you go back to your other slide 44, page 44, like that, where you look for these G mass calibrations. So Okay. Here is also 2 points. This low energy momentum measurement. Can we extrapolate to that high energy momentum measurement from the low energy momentum measurement data?
Well, I will keep insisting.
When we are talking about that 50 GeV, if 3 GeV my measurement is right, can I say that my 50 GeV my measurement will be right?
Well, first of all, we should not say energy. We should not say
Momentum,
energy.
PT.
No, we should say curvature. It's 1 over PT.
No, for the, okay, let's say calorimeter you measure the energy. So that's
Yes.
also, that's the energy. Yeah, so curvatures. So if the
here,
3 GeV it match, can we say that it will be also match at 50 GeV?
the right way to say it is not GeV. It is 1 over GeV.
Okay, I'm saying that when you go to this calorimeter, then it is GeV.
Yeah, okay, so now we go
Or
to the
1 over
calorimeter.
GeV, whatever it is, you go. Yeah.
So this is the calorimeter in GeV.
Okay, my simple point is how can we, how much we can trust that if I have a measurement at 3 GeV, I can say my measurement will be at 50 GeV also will be the same. There will be no bias, or 3 GeV if I have a bias, I will have a bias in 50 GeV. Whatever we measure. Can we tell
understand? That? Yeah, I understand your question, but I have to change your question. I'm going to change your question. The energy calibration is only applicable to calorimeter. So there you're calibrating 40 GeV tracks versus 40 GeV calorimeter.
No, I am not talking about that. I am talking, let's say, just concentrate only say mu.
Here, okay.
Okay, mu on channel.
Yes.
So at 3 GeV, you have a measurement, you say curvature. My curvature at 3 GeV is precise. Can I tell that my curvature will be at 50 GeV also be the same and there is no bias?
Yes, you can. Because it is not an extrapolation from 3 GeV to 50. It is an extrapolation in 1 over GeV units.
Okay.
It is the first point I have to come across here. The extrapolation is in this plot towards the left.
Yeah, that's the 1 by PT. So my point is that when you
Govinda?
go 0.4, okay, that's the point. Okay, but I do not agree with that. That if
Yeah, okay. So
I measure at 3 GeV, that we can say that 100 GeV also it will be the same curvature or momentum, whatever it is. Okay,
Well,
okay, that's fine.
Okay, I think maybe we just go on to the next question. Gagan, do you have a quick question?
Yeah, no, so sorry, maybe since I asked in between, if you allow other people and if there is a time I can ask, but I had only one question.
Okay, so maybe let's go to the people who have not yet asked. So
absolutely.
Okay, so then let's go to Kajari first. Kajari, can you hear me?
Can you hear me?
Yes, now we can hear you.
Yeah, of course. Very.
Kajari, your sound got cut again.
Could you go to slide 9?
9? Okay.
90, I think.
Last.
Yeah? Oh, 90. Okay,
yeah.
90.
So where you are talking about?
Almost there. 9. 90, the last slide, okay.
Yeah.
I can't hear Kajari.
What are the improvements? I don't understand.
Kajari, your sound is getting cut. So let's first go to Paul. Paul, can you ask your question first? And Kajari will figure out what the sound issue.
Yes, it's more of a comment of a possible theoretical interpretation. obviously there will probably be several theory papers if there are not already. But I have a conflict of interest, I must admit. But in the U3-1 model, you had mentioned an extended gate vector as one possibility. And in the 331 model, which the LHC is presently trying to find a doubly charged gate boson in same time lepton, there would also be a single charged by lepton, which is hard to find. This would connect with the W, and this rough, very rough estimate suggests that such mixing, which would violate lepton number, because the bilepton has lepton number 2 and the W has lepton number 0. But nevertheless, you need higher dimensional operators from LHC, and they would create a shift on the order of a few 10 MeV. So that's one possible theoretical explanation. This is Paul Frampton, by the way.
Hello, Paul. Good to hear from you.
Hello, good to hear your talk.
Thank you, Paul. Good to hear from you.
So I think Paul's question can be basically, maybe can we take it as a comment about the theoretical modeling? So in that case, I'll.
You mean in the chat?
Yeah, okay. So Kajri's question is on slide 78. What is the gray shaded region in the plot?
The gray shaded region are all the backgrounds.
Okay.
So in the muon channel, you will see the Z, this roughly 7% Z boson background is this region in the muons. For the electron channel, because you have EM calorimeter in the forward, the electron channel background for Z's is way smaller, much smaller. So if you take the backgrounds from that table, you see the sort of small background in the electron channel down here is the gray region.
Okay, thanks. So Kajri has one more question, but Sudeshna, let's take Sudeshna's question first. She didn't have a chance to speak. So Sudeshna.
Yeah, can you hear me?
Yes.
So I have two small questions. One is that, is this the full data set that CDF has? I thought a little bit more was there.
This is the full data set after requiring the quality requirements on the detector components we care about.
Okay, okay. So
Calorimeter and drift chamber has to be high quality operations.
Yeah, yeah. Okay. So that's why it's a little bit, yeah. Okay.
About 10%, yes.
Yeah. Okay. And the second question is this ResBos version that you used, you yourself said that it is from the older analysis period.
Yes.
So if it is improved, because these ResBos people have done more work and they have improved model now. So if you use that, I mean, is there any plan to use it?
We can always do more. So all the machinery is available. We have preserved it. So we can always do more depending on community feedback.
Okay.
So, but everything that you can do, you can make a long list. You can do this, you can do this, you can do this.
Yeah, I understand.
So, my comment for now is, it is always worthwhile understanding what the improvement actually is, which component of ResBos is trying to do better, and is that improvement already encapsulated in the fact that we are constraining ResBos to our data.
Okay, so that was my next question actually. So what is your comment about the amount of improvement?
So my sense, I mean, this is a long question, I'm condensing it.
Okay.
That given that we have included the boson PT spectrum from both the Z's and the W's, we have a constraint targeting the low PT region, which is different physics. We have a constraint targeting the high PT region, which is different physics. So now suppose ResBos is able to go from next to leading order resummation, next to leading log, they call it.
Yeah.
Suppose they go to next leading log.
Okay.
Which part of the spectrum will be better described? Is that part already within the region we are constraining with the data? So all that will end up happening is we will change one of those tuning parameters, and in the end, the plot will look the same. So
Okay.
same logic for the tail. We are using next to leading order exact calculation from the fixed order. That's the version of ResBos that was there.
Okay.
They, I think, have now next to leading order for the high PT end. But we are tuning something that tries to capture the lambda QCD or alpha S, whatever you want to call it. You can see the quality of the fit. So within that quality of the fit, if the theory calculation became more exact, the modeling, the tuning will adjust for it. So what will we gain?
Okay.
We'll just repeat the same thing with a different tune.
Uh-huh. Well, I
Okay.
guess people are
This is
asking
just-
this again just because this shift of the central value, but I understand your point.
Okay.
Yes, we would like to learn more about where improvements could come from rather than try every program one after the other, right? Then why stop at ResBos? We could try the second
Yeah.
program.
Yeah. Okay.
Okay.
Thanks.
So there are some questions by Shilpi Jain in the chat box. One question, the first question is, I understand that the value of alpha S, which is an input to ResBos, is constrained from the dielectron PT distribution in the data. Why is PDG value not used instead? And could that make a difference?
See, depends what you mean by could it make a difference. It will certainly make a difference to the theory prediction in that plot. But then what are we supposed to do? We have to then modify the theory in some way so that the model then agrees again with the plot. So if we change the alpha S value, maybe we have to change some resummation part somewhere, or we have to find some other missing piece of the calculation. I mean, all these calculations have missing pieces, right? They can never be 100% perturbation theory to infinite order. They're always to some order and some truncation is happening. So some other missing piece will have to be adjusted so that the theory comes back to look like the plot. What do we gain? Instead of adjusting one aspect of the theory, we will adjust a different aspect of it.
Okay. And the second question is on slide 44. Why does the combined measurement lie close to the Z boson measurement if that has higher statistics?
Let's go back to 44. Why does the
combined measurement lie close to the Z boson measurement if that has higher statistics? This is
lower C mean. I mean, letter C just.
okay.
Lower.
Yeah.
So let me explain what is being done here. There is the number from the blue line, sorry, the black line. So the black line is the number from the J psi. Right? So all the J psi get encapsulated in this one black line. So now consider the black line, the red point is the epsilon, and the green point, which is the Z. So this purple square, this purple cross, this purple cross is the average between the green, the red, and the back line. Yes, you see?
Yes.
And so the average means all the systematic uncertainties and everything. So you have to take these tables, take the systematic uncertainties from all of these, put them together as an average of the black line, the red point, and the green point.
Yeah, so I think it's also the black line which is causing it. So it's not so clear.
Yes, yes, it's the.
Okay. And finally, the third question is, how robust is the electron energy scale as a function of PU? I can't understand this question, but
Pile up.
Okay.
Okay, so it's a little bit. Here's what we did. So this is again an improvement that was not done in the past. The fit for electron energy versus track momentum, that quantity of the ratio, was actually calibrated as a function of time for each tower. So during the running, the pileup is changing. So that means we are adjusting for the pileup during the calibration process. I am skipping some details here because, okay, for the sake of time. So the things that would affect the electron energy scale as a function of pileup, as a function of degradation of the scintillator response, all the detector effects which are time dependent, those have already been calibrated out by using the track energy to calorimeter energy ratio. So now the answer is, it's already been corrected. So there is no way to answer, right?
Okay. So next is Nishita, and then after that Arnab, and then we'll cycle back to the old questions. Nishita, go ahead.
Yeah, thanks. So thanks for the very detailed talk. So I had a question further about the contribution from Monte Carlo. And if I understand you correctly, there is some tuning going on to match between ISR and resummation and so on.
Yes.
So just to pinpoint what is going on, I was wondering if you had an exercise where you simply move the central value to the world average and ask where does the mismatch show up, just to understand whether it's in the resummation part or the ISR part, or where exactly would it show up?
The world central value of which quantity?
Of the mass, or rather empty in your case. I mean, the empty distribution corresponding to what the world average would be. That's what I meant. So you use the expected shape from that.
Yes.
And compare it to the shape that you have from which you've extracted MW.
Yes.
I'm just wondering where exactly the mismatch shows up. Is it in a particular region of it? So can we say that the ISR part is not doing the modeling correctly, or the resummed part is not doing the modeling correctly, or something like that?
I'm hearing two different distributions in your question, because when you talk about ISR and so on, I think you're talking about the boson PT spectrum.
It could be boson PT or lepton PT, either of them, right? I mean, you can, and also you can get MT from with ISR. Okay, so maybe there is a mismatch in the vocabulary that is being used. So since I'm talking from a theorist perspective, but
yeah, I'm trying to understand your vocabulary.
Lepton.
Yeah, okay, maybe let's talk about in terms of just lepton PT distribution. Okay. So what I'm asking is, if you look at the lepton PT distribution, just Monte Carlo, not looking at data,
yes,
from two different values of MW, you would get a different, slightly different. Yeah, exactly. So here, exactly. So this is exactly the distribution that I was talking about.
Yes.
So you have the transverse mass on the x-axis, right?
Yes.
And if you have different MW, then you expect a different curve.
Yes.
Right? So I'm just saying that using the world average for MW and what you have as the best fit, where exactly is the difference?
It essentially will follow this pattern. So you see an illustration of your question here, right? Mm-hmm. This is two different MWs. And you can see how the distribution red versus blue is changing because of MW changing. So you're asking now, when you observe a difference like this, one distribution is a little more to the right on the edge, and therefore it's lower elsewhere. Can you use this shape difference to actually infer anything about the input variation? Is it input coming from ISR or this or that?
Yeah, exactly. So, I mean, I'm just trying to pinpoint whether going to a higher order or having a better, say, merging procedure would solve the problem. That's the only thing that I'm trying to gauge.
It is very difficult to do an analytic conversion from all the things we talked about here into a corresponding contribution to a particular region of this spectrum. This spectrum is a very elaborate, non-analytic convolution of 50 different things. So there is no way to map a region in this plot to some physics thing somewhere else. No way. It's built into the logic that you have to do this with a Monte Carlo. I mean, that's exactly what a Monte Carlo will do. It will do some enormous multi-dimensional convolution for you and propagate all input effects into this one plot. You cannot reverse that. It's not a reversible mapping.
Okay, thanks. Arnab, could you go ahead?
Hi, can you hear me?
Yes.
Thank you. First of all, thank you for the nice talk. I have two questions. One is, do you use Kalman filtering technique for the track reconstruction?
No, much easier.
Okay.
It is simply taking the outermost region of the track, defining a narrow road, goes to the next inner region, defines a narrow road, but there is no fancy updating. There is no energy loss updating and all the other, clever things that Kalman filter does. No, there is no clever tracking here. It's in some sense nice and simple tracking.
May I know why is that not used? I mean, is it enough to use a simple method?
It's much better. I will make an argument here that rather than elaborate the tracking and then having to mimic all the tracking elaborations in the simulation, and then you start asking the question, is the simulated tracking an exact duplicate of the actual data tracking, which is not an easy question to answer. It is much better to have the treatment of the data simple, and then you model the real physics aspects of the detector in the simulation. Another way to say the same thing is, do not build in elaborate corrections in the data. Build in all the elaborate physics in the simulation, make the simulation like the detector, but the data treatment should be kept simple so that that part is easy to duplicate.
Okay. Okay, so in that case, I mean, your material, the material budget in the tracker is, you mean it's well simulated?
Yes.
Very well. Okay.
Yes, and you can sort of see that if that was not well simulated, you don't gain anything by doing Kalman filter, because Kalman filter will use that same inappropriate calculation. So Kalman filter cannot fix a mistake beyond what you tell it to do.
Yeah.
So you see, it doesn't help anything because it doesn't gain any new information that you don't already know.
Okay. And my next question is, do you use vertex information for for correcting the momentum?
Yes.
So for that, you do the vortex fitting and then use that, or you just use the beam spot as a whole and use that information?
Very good. I see a difference. Yes, at the latter, we use only the beam spot because we are looking for W bosons that decay promptly.
Yeah.
There is one lepton coming out of it.
Yeah.
And the rest is all junk flying around. So only beam spot is necessary.
Just related to this, I mean, so what I understood is the electron momentum resolution is highly driven by the tracker. I mean, it's
yes.
But what about the muons?
Also driven by the tracker, but much better because the radiation, photon radiation effects on the muon are
yes,
smaller.
Of course, yes. Thank you very much. And these are the questions.
Tuhin, would you go next?
Yeah. So first of all, I mean, that this wonderful talk, not just wonderful talk. I mean, there was a superlative analysis that you guys did. So just congratulate for that.
Thank you.
So being a cynical theorist, I can't stop myself from asking, there is, I mean, what you have, what you are fitting, for example, the data taken over a long period of time, right?
Yeah.
Is there, I mean, if you ask yourself this question, is it something, some systematics, if, that is unaccounted for, like the deformation of the detector itself with time and things like that? Is there a way that you could confirm, or do you have an intuition regarding this?
Good. So we went at this question from tracking to calorimetry for EM calorimeter to hadronic calorimeter. We went down what you are asking basically as a checklist, shall we say. Let's go for tracker time-dependent effects first, then go for EM calorimeter, time-dependent aging, whatever goes on second. And then the most diffuse, most random fluctuating quantity, which is hadronic recoil, which is therefore least sensitive to time-dependent effects because it is intrinsically ugly anyway. So that was our priority ordering, which to us made some sense. So therefore, we checked the alignment of the drift chamber most precisely with the cosmic rays, split it into run periods, see if the beamline centering was as good as we could do, reconstructing the data over and over again in subsamples and all of this. That led us to one assurance, and found it adequate, so we could move on. That assurance is, why is this stuck? That assurance, here. If you look at the last row, this is, it's a complicated thing. So we did 2 run blocks to see if there's any obvious problem. That's the mass of the Z boson, which is our independent cross-check in 2 run periods, half and half. So half the data before, half after. You see this level of consistency in the muon channel Z mass, this level of consistency in electron channel. Okay. One more. Upsilons, I think this gets back to instantaneous luminosity pileup. The 2 numbers at the bottom of this page is the momentum scale measured from the upsilon. So you can see 23 parts per million is very precise. Splitting the upsilons into first half and second half, or splitting the upsilons between lower instantaneous luminosity, which is low pileup versus high pileup. The thing is, those 2 are not really independent because initial data is low pileup and later data is on average high pileup. But otherwise you have to do it 4 ways. Okay, we could do it 4 ways. All right. So this was telling us drift chamber was pretty well constrained. We don't see any source of problems in the time dependence of the drift chamber. Then we go to the EM calorimeter. So there, obviously, we start seeing time dependence because it is well known scintillator calorimeter is not stable. So we take our own data and say, okay, let's start calibrating. There is a first pass done by low quality electrons, junk electrons from conversions and things, very high statistics. So you do a first pass there, you get it down to I would say 1% or better, 0.5% uniformity. Then you take the electrons from the Ws themselves and you can get down to maybe 10 to the minus 3 level. The final precision is 10 to the minus 4 level. So at this point, we don't trust the junk electrons to give us 10 to the minus 4. We only trust the Ws, and there the statistics get us to uniformity at the level of 10 to the minus 3. So it's sort of okay, right? The average is 10 times better than some fluctuations you can observe is not so bad. I don't know how you would do better. So the remaining part which we'll have on our list is, can we do time-dependent calibrations of the hadronic calorimeter? And this is where we stopped. So that part of the analysis continues to be inclusive. The whole thing was always inclusive from the very beginning. We made it as exclusive as we could as time went on. So if you ask me some dream question, if you had 5 more years, the experimental part that we would redo is go back to the data and do the hadronic calorimeter calibration as a function of time.
Okay.
Explicitly build in all pile-up dependence, degradation of scintillator, everything you can think of, and then rerun the whole thing. So that, I don't know if you should call it a goal. It's a wish list.
Okay. Thanks. So Gagan has a question and Kajri has a question. I think that's all. Thanks for being so patient.
Right. I'm sorry. So yes, indeed, I am being an experimentalist. I'm really happy to see that whatever you have achieved. And since I had asked lots of questions in the beginning, just one question I had. This is related to the science paper. So you have this 6 or 7 measurement table number 1.
Yes.
So now the question is, each of the I trust my theory colleague, but each of the observable from which you are extracting the W mass, the theory uncertainty for each of them can be different, and particularly. So the question is, when we do average all of them together into one big piece, and in fact, that there is a PRD paper, quite a few papers, like some people are trying to say that whether the theoretical uncertainty that we have. So what I was asking, that did you try to have sort of theoretically cleaner measurement, and then that average, sort of separating them into 2 subsample and then seeing that how the total uncertainty would look like in each of them, rather than adding them together?
There is a table. Okay, so it's a combination. It's a combination of this table where the theoretical uncertainties are different in the 3 things you can fit: transverse mass, lepton, PT, neutrino. Different theoretical uncertainties. Now you can combine. So the combination you're looking for may be here. If it's not here, we can add it and somehow put it out separately. So
I want theoretically clean thing. I am scared of the theory uncertainty like playing out.
So the theoretical uncertainty that matters the most is the production level uncertainties in modeling the W production. The other theoretical uncertainties are in the electroweak sector. I mean, the photon radiation and loops associated with W and Z bosons. So heavy boson loops are also there in the electroweak part of the vertex. And there is some interference between that and the real photon radiation and all of this. That all the 3 fits have the same. So on the QED side, to the whatever discussions we had with all our theory colleagues in the past, they didn't tell us that anything was different in the 3 fits from the electroweak side. So on the QCD side, historically the theory uncertainty was largest in the lepton, less so in the transverse mass. And the corresponding trade-off, nothing is free, right? There's always a trade-off, was that the detector sensitivity, detector calibration was more sensitive in the transverse mass and less in the lepton. So which one do we what we control better is the detector calibration.
Yes.
We don't control as well as the theory. So
Yes.
historically, the perspective from the experimental was it's the transverse mass that we think is the most reliable. That's our perspective, obviously, right? Somebody else can have the opposite perspective. So it's one of the reasons why we do them all and just show everything. If you like to pick and choose, you can pick and choose.
Okay, I would leave only the theory uncertainty on each of them, but okay, that's fine. Thank you.
Kajiri, can you ask? Yeah, good.
Can you hear?
No, it comes and goes. It comes and goes. So maybe you can type it.
Typing several times.
Okay, sorry. Yeah, what is
improvements? What are?
Yes, that's right. What are the specific improvements in the recent analysis?
Okay, so this table is from the paper. We were able to make these 15 improvements, and the first two you will see we were able to quantify. In other words, what would happen to our old measurement from 2012 if these improvements were also made back then. So this was quantifiable by running simulation and checking and rerunning data reconstruction and so on. We were not yet able to quantify the improvements that we were not able to quantify the rest of these improvements as to what impact they would have. This table, it gives you, this is from the paper. If you go to the corresponding section of the paper, then every one of these is explained. So I have a few slides. I don't know if you have time to read them all here. So every one of those improvements is explained here briefly. Long list.
Okay, thank you. Because I have.
Can we have your slide available to receive or someone so that if we want to see this thing in detail, is that possible?
Yeah, so I have it. I'll put it on the Indico page, and you can by tonight you'll be able to see it.
Okay.
Okay, so I think Kajli can. Okay, go ahead.
Sorry.
No, I said that I.
Kajiri, you are getting disconnected continuously.
I don't know.
Yeah.
I will read the.
Yeah.
Okay.
Yeah. Okay. Bye.
So, well, Arnab, do you have a short question?
A very short question. So,
okay.
Thank you for considering. So, if we go back to the MW measurement with comparison with respect to the past results, I forgot which slide it was. I mean, like it's the main result that was, yeah, this one. I mean, like I don't know if it's true, but it seems like CDF I and CDF II, the best fit measurement is almost the same. Is it a coincidence?
Yeah. The precision going from 79 MeV to 9 MeV with this kind of change in precision and analysis technique changes has to be coincidence. This analysis from 2001 onwards, what we call the run 2 analysis, has been completely started from scratch. The CDF I analysis was completely different analysis code, simulation, everything was completely independent. None of that was used as a starting point. This starting in 99 or so, this was started completely from scratch, every piece of it. So coincidence.
Okay, thanks.
Okay, I think we should wrap up. Thanks a lot. This was a really wonderful talk, and hopefully we'll see you sometime.
Yes, certainly. Looking forward
Thanks
to
a lot. I think we should also thank the speaker.
Okay.
Thanks.